Ladies and gentlemen, please take your seats. Our program is about to begin. Once again, please take your seats. Our program is about to begin. Thank you. Ladies and gentlemen, our program is about to begin. At this time, please take your seats. Once again, our program is about to begin. Please take your seats. Thank you. Ladies and gentlemen, please welcome back your host, Andy Konwinski.
Thank you, and welcome back to the second day of Spark Summit here in Amsterdam. If you remember yesterday, we talked about 3 reasons people turn out for the summit. We're technology, community, and business, but especially in the context of the enterprise. We're going to see that theme reinforced today. And yesterday, we saw it in the keynotes and the talks in the afternoon. One of my favorite talks was the Goldman Sachs talk, Vince Solis, who spoke about how Spark was getting traction inside of Goldman Sachs. I thought it was impressive to hear the technology investment in platforms that Goldman makes and how seriously they're taking Spark. I especially liked that Vince is an R enthusiast and spokesperson inside the company, and that he's turned or added to his portfolio of technologies that he evangelizes inside of Goldman Spark. So you can see the relationship there that R and data science, as well as Spark, kind of getting a lot of co-traction inside of organizations. Something, especially as an organization as exciting as Goldman. I also really liked the talk in the afternoon by Aaron Davidson on 100+ uses of Spark. Seeing all the different types of traction that Spark is getting, again, reinforces that theme. Something I got feedback on from yesterday morning was that people liked the interaction with the audience, so I brought an actual microphone with me this morning, and I thought we would see if anybody would be brave enough to volunteer what their favorite session from yesterday was. And the motivation behind interacting a little is that it's easier for all of us and actually sticks to the theme of community and our culture as a project to think of the summits like really big, slightly more structured meetups, which is another one of the backbones of the Spark community. So I'm just going to jump off the stage and see if anybody's brave enough to say what their favorite, or actually either what your favorite thing from yesterday was or something you learned. Somebody right in the front row shows themselves. Sure.
Hi, my name is Christian Grant. I was just amazed about the PC personal cluster, a small, tiny cluster that was exhibited in the showroom. What it needs is probably a little Apple design, but otherwise it would get one.
Great. Anybody else?
Hi, Praveen.
Stand up. Praveen.
Hi, Praveen from CSC. Yesterday the talk about ANNs, the implementation of it in Spark was quite interesting for our use case because we are currently experimenting a lot to integrate them in the PySpark environment.
And what is the summary of your use case? If you can do it in about 10 seconds.
It's about transportation chain and estimating the ETAs in a graph problem.
Awesome. Great. Thanks. One or two more? Walk past the first row. Stop at this row. Oh, great. Stand up, please.
Yeah, hi everybody. This is an amazing conference, so a lot of good speeches, but yesterday I liked it most, the one about Spark Job Server, because that one will help us to put everything into production really quickly, and we really think we'll use it. So thanks a lot.
Thanks a lot. Josef?
Yeah.
Great. All right, so thanks a lot for your interaction. It's great to hear about use cases like that. This morning, we're going to see in our keynotes that theme of the enterprise traction reinforced again, but with a slightly different take thematically this morning. We're going to see that as we enter the enterprise as a community or as a project Spark, we're interacting with other frameworks and platforms that enterprises are adopting. And this will show up in at least 2 of our keynotes, including this first one, Scala and also Cassandra. So let's kick it off and shift gears by, I'll introduce our first speaker. Our first speaker is the creator of the Scala language, Martin Odersky. He's a founder at TypeSafe and professor at EPFL. And I remember the first time I had the privilege to meet Martin was actually with Mate. And it was long before we had started Databricks. It was just when what was then Spark SQL called Shark was looking at ways to do the in-memory columnar storage. And there was, it was a point of innovation for the project. And I remember how excited Martin was. I think it was Scala 2.11 or maybe 2.10 where he was actually talking with us about some of the features that the language was adding that he thought would be great for Spark to use, and that would add sort of to the iteration or the collaboration that the two open source projects could go forward with. And I think that that conversation has stuck in my memory as symbolic of the way that open source communities can overlap. The leaders inside of them are often and almost always in touch at various points throughout the organization on all the different levels that a community consists of. And in the case of Spark and Scala, the actual synergy goes very deep. Spark, as we heard actually in Vince's talk from Goldman yesterday, Scala is sort of emblematic of the way we think about programming in Spark and has been since day one. So it's really, really a privilege to hear from Martin today and his talk titled The Ultimate Scala Collections. Let's welcome Martin to the stage.
Okay, thanks for having me here. It's a great pleasure to speak in front of so many Spark enthusiasts. So the title of my talk is Spark, the Ultimate Scala Collections, and I realize that's maybe a little bit provocative. For those of you who don't know Scala, let me just slot it in. It's a functional language, also object-oriented. It's statically typed, and it's designed to interoperate very well with Java and recently also JavaScript. But that's kind of boring. It's just a categorization. The more important part is what were the main design principles, so the invariants that went through all of Scala's design and that made Scala the language it is. And I think there are two. The first is really this idea of a scalable language. So Scala has flexible syntax, flexible types, user-definable operators, higher-order functions, implicits. It's a whole bundle of tools to really make it very easy to build domain-specific languages on top of Scala, embedded into a Scala runtime. And that design principle has been spectacularly successful because there have been a large number of domain-specific languages that were sprouting up with Scala as essentially the seed. So two of them came out of Berkeley. That's Chisel for hardware design and Spark, which of course you all know. A series of them came out of Stanford. That was the OptiX series of languages for staging. And then you can also think of, for instance, SBT, the Scala build tool, as a domain-specific language. Spiral, essentially for program generation of very, very fast algorithms, is another domain-specific language running on top of Scala, and so on. So there's a whole lot of them, but of course today we're going to talk about Spark, which is in a sense the most widespread, the most successful of all the DSLs that you see here. So Spark is clearly a domain-specific language. It's a language for data analysis and big data. It's implemented in Scala, and it's embedded in Scala as a host language. So what you see here is the Spark runtime runs on top of the JVM, and in between the JVM and the Spark runtime is the Scala runtime, essentially a standard library, the runtime modules, and then of course it connects to file systems, cluster managers, and so on. But the embedding is really deeper than that because there's also a layer on top of the Spark runtime. There's the REPL. That's everybody who uses Spark from Scala uses the REPL to essentially write the queries. And that REPL is just the Scala REPL. And the REPL, in turn, to do its work, needs the services of the Scala compiler. So when you write a Spark query in Scala, then actually all these components, they work together to give you the result. So there are two reasons for domain-specific languages that we can see. Quite a few of them are there because they want to essentially support new syntax, add another language and essentially Scala is a cheap way to implement that new syntax. And the second one is to support new functionality. And I find the second one much more interesting than the first because essentially that's where you go deeper. You're not staying just at the surface. So Spark is clearly an example of the second kind. So it actually is very conservative with the syntax, and I think that's one of its strengths, that it can just reuse a lot of things that we know from Scala, but it adds really powerful functionality. So the functionality is centered around collections, and the view of collections in both Scala and Spark is that they are immutable data sets equipped with functional transformations. And here you see some of them, which you of course all know from the Spark side. But if you're a Scala programmer and know nothing about Spark, then you know them also because these are exactly the Scala collection operations. And that, I think, was a very big, very nice confluence of ideas and very nice reuse of essentially brain power. So is Spark then exactly Scala collections but running in a cluster? Actually, no. There are two differences, and I think the differences are important. The first is that Spark is lazy in its way it treats collections, and Scala collections are strict. And the second one is that Spark has some added functionality, in particular when it comes to pairs, the concept of pair RDDs. So if I take a step back and say, well, what kind of collections are out there, collection libraries, then I think the first distinction is between the imperative collections that you know, for instance, from Java util, and the functional collections. Imperative, of course, is much more common. Almost every library has one, because imperative programming has been mainstream for much, much longer than functional programming. But functional programming is catching up. So once you go functional, then you have another distinction, and that's the question whether you're lazy or strict. So there are strict functional collections. For instance, the default collections in Scala are that, or OCaml is another language which would give you strict collections. Lazy collections you find, interestingly, in C#. LINQ is fundamentally lazy, also Spark, and there are some specific Scala collections that are lazy. So what's the difference? The difference is best seen in a small example like this one. Let's say you have a function data.mapf, and you put that in a value XS, and then you filter on the result, and then you take the sum, and then you have another operation on XS where you just take the first elements and print them. So in a strict collection library, the map would be evaluated once, and the result of the map would be stored in the value XS. In a lazy collection library, all the map does, in a sense, it gives you a recipe how to compute the result. It doesn't actually compute the result. So XS would contain that recipe, and then map would be evaluated twice, once when you follow it up with the filter operation, and once when you follow it up with the take. Laziness gets very confusing when mixed with side effects. So there's a paper by Eric Meyer that argues this point very strongly. So typically, to be predominantly lazy, you want a purely functional architecture. You want really to have basically no side effects in your program. But that's the use case of Spark. There are no side effects typically. It is a purely functional architecture. So laziness makes a lot of sense. The other reason where strictness makes sense is if I only look at the first line, I just want to do a simple map, then really I want the result. I don't want to be concerned that, no, this is a recipe for the result and I have to force it or things like that. So that simple use case is strict is actually better. Now, in Spark, you probably wouldn't have a simple map. You have always more involved queries, and therefore the laziness makes a lot of sense because then you can optimize much better. But for a Scala program, that's actually the most common use case because, I mean, programs are often relatively trivial. You just want to do a simple thing and then do the next step. So that's also why I think do optimize a simple step case. Strict in the programming language is actually a good choice. But on the other hand, I think laziness is really very, very important for the more involved use cases. So what we are about to do currently, we're sort of in the evaluate proposal stage, is to redo the concept of views for Scala collections. So here's how I would get the lazy behavior of Spark in the next version of Scala collections, hopefully. I would write XS, and then I would write .view, and that turns it into a lazy collection. So now I have recipes, now I can do a map and a filter, and I won't create intermediate results, I will just add to the recipe, and then at the end, I write force, or I can actually convert to a collection that of my choice when I want to change the collection with a .to. And another thing that I think we will gladly copy from Scala, from Spark, was this idea to use cache to essentially persist a view. I think once you have views, that's a very, very good operation, and so far it was missing in Scala. So add cache to it and therefore get views somewhat on a par with what people can do in Spark. The other thing that makes a lot of sense and that we will happily copy over to Scala is the pairwise operations that we see in the Scala collection libraries, things like reduce by key, group by key, lookups, and these would work on sequences of pairs analogously to pair RDDs. That, of course, is nice because it provides a very lightweight way to add map-like operations to sequences. You can write equivalent operations in Scala today, but they are clunkier. You have to introduce a map and then do the operations, and sometimes it's several steps where this, in the Spark library, a single method suffices. Good, so that was the first design principle, scalability, how it relates to collections. The second one is, in the second design principle of Scala, it's really that it's all about the types. Types are first and foremost in the language design. They're the hardest part. They're the part that most of the deliberation went into. And when we talk about types, then we often see a trade-off in the industry and in research, and the trade-off is between safety and flexibility. So if you want to have maximal flexibility, then you can make do with just a single type, or that also is called an untyped language or a dynamically typed language. Then you're maximally flexible. The types will never get in the way, but you're also, essentially, you threw out all the possible safety guarantees that a type system can give you. On the other side, on the vertical axis, if you want to be maximally safe, then you write your program in an essentially theorem prover like Coq or Agda, and that way you can actually prove the correctness of your program in the type, but of course it will take you sometimes a long time and a long ramp up to be able to do that. So it's always a trade-off between the two. And the goals of programming language designs or the trend in type systems has recently been more towards safety. So we see essentially Scala is maybe some part of that, but more importantly, you see that in languages like Haskell and Idris and Agda, where essentially you push the boundary of safety, which I find really fascinating. It's a great development, sometimes even at the expense of ease of use. You say, well, this might be good in some cases, but in most cases, really, it's not a good idea, so we will take it away. Scala has been so far on a different trajectory, where we say, well, what we really want to get is a good amount of safety, sort of the state of the art in safety, maybe not the cutting edge yet, at the flexibility that you could get from a dynamic language. So we wanted to push it sideways to say we want essentially to get that safety and not give up any of a lot of the restrictions from a dynamic language. That's why some of parts of Scala actually feel rather dynamic. For instance, the actors are even untyped. Well, they have type any in the messages, and then you get the types with pattern matching. These are sort of things that, for better or worse, are very, very dynamic, very, very flexible. They're maybe not super safe. It's a trade-off. But Scala was deliberately pushing into that direction. Okay, where we'd like to move it in the future, of course, is all encompassing to say we want to be not give up any of the flexibility, but get a lot of more safety in the future, for instance, by tracking effects and things like that. So, but that's sort of ongoing work and work that hasn't really hatched yet. So Spark, of course, is a multi-language platform. Scala is not the only citizen on Spark. There's Python, which is very popular. There's Java, there's R, there's SQL native. So one should, of course, ask oneself, well, why Scala and not one of these other languages? Or what are the advantages of Scala over, let's say, Python? So one thing I believe is, well, it's native to Spark. Spark is written in Scala, so if you want to go as far as maybe add a module to Spark or understand what goes on in the source, then Scala is an advantage. But the second and more important one, I think, at least from my perspective, you might disagree, is the types help a lot. Because if you once you have these collection operations, the types give you these guardrails where you say, well, it's almost impossible to make a mistake that is not caught by the type checker. And I'm maybe too squeamish. I would be very nervous to try to do these things without the help of a type checker to catch me out, to catch my errors. Because the types help a lot because it's functional. This combination of static typing and functional collections is really very powerful. Why? Because the functional operations, they don't have any hidden dependencies. That's the definition of a function. It takes inputs to outputs. There's no side effects. There's no hidden channel. Now, if you type check both the inputs and the outputs, as you do in a statically typed language, you have a very, very dense safety net. So every interaction is given a type, and that means that logic errors usually translate into type errors. Those of you who have used that, I guess you agree with me that you can write hundreds of lines of code and not have a single error once it passed the type checker. And that's an experience I never had before because I wasn't really that pedantic as a programmer. I always had these mistakes and then I had to go into debugger and it was hell. But nowadays I just run it through the type checker and life is good. So it's a great asset for programming, and I think the same should hold for data science. I know that data scientists are sort of used to more languages like R and Python. That's where they come from. So, but I believe even if you do data science, then types should be a great asset too. So what we've seen so far is essentially what Spark and Scala are. How can Scala help Spark in the future? So I think there are several things that we can work on and will work on. One is the developer experience, the infrastructure, the spores, and diffusion. Let me quickly talk about some of these points. About the infrastructure. So let me put up the design again, how Spark is sort of embedded in the Scala system. What should we, TypeSafe, and the Scala community work on to actually help Spark? So one thing we have worked on is the Scala REPL, where we had a problem before, mostly having to do with versions of JLine. JLine is this thing that every REPL uses because it does essentially these basic line editing commands. And unfortunately, there are many different versions and they're incompatible, and Spark used one and the Scala REPL used another, and that's why the Scala REPL had to be forked for Spark to actually use a different JLine. So what we did was make JLine more pluggable, more auto-detectable. So that's a thing of the past. So now we can actually use the standard Scala REPL again. And the big advantage is that then Spark also profits from some very nice developments that have recently been done on the Scala REPL, namely that the Scala REPL is now much more tightly integrated with the Scala compiler to give you things like auto-completion that are on a par with things like in the IDE. Before it was clunkier, and now you get the same level of auto-completion that you would see in IntelliJ or in the Eclipse IDE and things like that, because it goes out to the Scala compiler for the services. So that's essentially the advantage of not forking. You profit from each other's developments, from each other's improvements. Scala compiler, it's the auto-completion, but also, of course, the thing to, when we want to move to Java 8, we are compatible with Java 8, but in the next version, we want to profit from the advantages that Java 8 brings us. And those advantages are first the use of lambdas, so no more inner classes. Lambdas are more compact and faster. And second, the use of default methods. Default methods means that you don't need to write forwarders for traits anymore in Scala, and that together they mean that your Scala jars and class files should become much, much more compact. So that's a way we can actually make use of Java 8 to shrink the size of Scala executables and also to make them a little bit faster. The third area is the Scala runtime, where we're working on serialization and also integration with Java 8 streams. So the second aspect has to do with serialization also is spores. So one problem that Spark experienced several times, or at least we heard about it repeatedly, is the problem of how to send closures over a network. So closures are essentially function values that also have to come with everything they reference. And they use Java serialization. And Java serialization is kind of unpredictable. So it can lead to very, very large dependency graphs. So an example you see here, you have this class, and it contains a data field of some very large collection, and then you make a function value sum, which is data.sum, and then at some later point you want to print just the sum, not the data. And what you do is you pass the closure, the function from x to println sum to this method doLater. So that closure gets built, and if doLater runs on a different computer, serialized over the network. The problem with that is that the closure will actually retain a pointer to the class, to the object of class C. And everything in that object will transitively be retained in the closure. So that includes this some large collection. And probably when you wrote that closure, you never thought that could happen. So these things really are big surprises to developers, and they're bad surprises. So what we would like to do is have closures be much more safe and safer for serializing. So the right way to write the closure to doLater is the way you see it here. So what we need to do is we just need to have this local computation that says, well, take the sum and put it in the value s, and now the function in the next line would close over s. So it would refer to s and no longer the self-pointer of the class C. And that way the closure would have an environment that consists just of a single number. So it would be very small. The tricky bit is, of course, programmers can do that today, but for doing it today, you have to sort of know where the traps are and put in the remedies. And you don't know. Serialization is completely opaque, so you don't see what it does. So the solution to that we have worked on is to have this concept of a spore, where you say you put then the closure in a thing called spore, and in the spore, spore typically returns with a closure, like you see here on the last line of the spore, but the spore is a macro that makes sure that this closure will only use values that are local to the spore, nothing outside. So everything that gets captured by the closure must be listed in the value definitions of the spore. And that way you can be completely safe, because if you have a hidden dependency, the compiler will tell you and will say, no, that's an error. So spores are, in a sense, closures that can sort of travel over the network and be safely sent to other places. Okay, that was number 2. Number 3 is Fusion. So in the earlier Spark summits this year, Kai Osterhout had a talk that a lot of Spark jobs are compute bound. There was the talk, Making Sense of Spark Performance. And of course, lazy collections avoid the intermediate results. But there's still an overhead, because even if your collections is lazy, you have each operation is a separate closure. And you can't look inside the closure. It's an opaque object for the library. So all you can do is just call this and call that. You can't really fuse these closures together. Spark has now solved this problem with data frames. So data frames are essentially a way, a domain-specific language to look inside closures, to look inside everything. But the restriction of data frames is essentially it only supports the operations that are supported by data frames. You can't use all the operations in your underlying language for that. So Fusion essentially attacks the same problem. So Fusion cuts through this. It can combine several closures in a tight loop. Spark implements Fusion for data frames, but we would like the same for general Scala code. So what we've worked on here is a project called the Dotty Linker. It's a smart whole program optimizer. It analyzes and tunes the program and the dependencies, removes dead code, eliminates virtual dispatch, eliminates boxing, eliminates closures. It can do all that because essentially it sees the whole program, and that gives it much more knowledge about essentially what goes on in the program. So just one example to show what it can do is that's a PageRank algorithm, 80K nodes. And you see that first the bytecode went down from 60 kilobytes of the app and 5.5 megabytes of the library to just 920 kilobytes. So it shrank a lot. Objects allocated is 1/6, virtual call is 1/8. CPU branch miss rate is 1/4, and running time is about 1/2. For a general purpose optimizer, this is actually pretty good, because while you can do a lot when you stay on very domain-specific operations, for general purpose optimizing, that's currently probably very, very good, in particular because it is combined with the JIT, and the JIT, of course, the JVM JIT also does a lot of optimizations. So this you get on top of the optimizations of the JVM JIT. Good. So just to conclude, I think Spark and Scala are beautiful examples what can be achieved by a bunch of dedicated grad students using a language and system originally written by another bunch of dedicated grad students. And I'm looking forward to the next steps of the co-evolution. Thank you.
Thanks a lot.
If there are questions, we still have some time.
Sure. We can do a small Q&A session if people have a couple of questions. Let me grab the microphone. Sure.
Hi.
Can you stand up?
Oh, sure. Hi. I want to know if you have any plans to add C or C++ like packing for Scala class objects and also the multi-dimensional arrays, which will help for different hardware platforms. It will be a great help.
Right. So directly we're hampered a little bit by running on the JVM. So essentially we can do that better if we don't run on the JVM, and there are essentially two ways to get that. One is essentially this series of the OptX languages that we did with Kundry Olokotun's group in Stanford, which is research, which uses staging, essentially something very similar to data frames, but now for the full language, and then a number of backends. So the backends could be a cluster, typically a supercomputer backends or GPU backends or things like that. So then you can, of course, do that, but that's sort of a special kind of compilation where you say you compile it and then you stage it. That means at runtime or at load time there will be another compiler that does then the mapping. The other thing is we currently have a project to go to have a backend that's LLVM based, and I would be very interested to get feedback on that. So essentially what would be possible use cases, who would be interested in that, and so on. So that's also very, very early stage right now. So I guess the answer, what you can use next year, no, probably not. But for later, it could be.
Hold on, let me give you the microphone back.
Okay.
I was also interested in asking about approach Spark unsafe, which is the Project Tungsten, which is what Project Tungsten uses.
I didn't.
The Project Tungsten in Spark, they
Tungsten,
use
yeah.
sun misc unsafe
Yes,
explicit.
yes.
So I was also asking about that, whether that can be used for packing.
Yeah,
objects.
absolutely. I think that would be a big thing. We should have a look at how we can maybe use that, because I think off-heap is, of course, a very, very common use case now. More and more people need it. Yeah.
Great. Well, I'll cut off questions there. I'm sure there's no shortage of questions. We'll just move along to stay on time. Thanks a lot.
Thank you. Thank you.
So I knew this talk would have no shortage of questions and it really dawned on me yesterday that the popularity of Scala in this particular section of the Spark community, there was, I think, a mention by one of the speakers, maybe you would call it a plug for using Scala over Java in Spark, and spontaneous applause broke out. And I must say that that is the first time that I've seen that sort of reaction to the proponent or to the advocacy of Scala over Java. And I think it's great for the community, and that makes it all the more powerful to have Martin speaking about the synergies between the two projects. So next up, we have the VP of Marketing from Cloudera, so Alan Saldik. And Alan's been an entrepreneur for 9 startups now. For the last 4 years, he's been at Cloudera, and I'm happy to say that he is a Berkeley alum, Go Bears, which maybe doesn't mean that much to a lot of people here, but it does mean a lot to the Spark project, having been incubated and born inside UC Berkeley. So let's welcome to the stage Alan for his talk, which is entitled Spark in the Enterprise 2 years later. Welcome, Alan.
Good morning. I'm amazed so many of you are here. There's a lot of distractions in Amsterdam. I am not Charles Zedlewski. Charles was originally scheduled to appear, but he had a lot of travel problems and canceled flights. I think they were trying to schedule his flights using MapReduce, and it just took too long, and finally he gave up. This is the only audience in the world where you can say something like that and get any kind of response. So Cloudera, we have been supporters and enthusiasts of Spark for quite a long time. In fact, right around 2 years ago, Mike Olson, our founder, wrote a blog post about Spark and how it was really the eventual replacement for MapReduce, and we continue to believe that very strongly. This timeline just shows a lot of the highlights of the last 2 years for Cloudera, things that we've been working on with Spark. We've been shipping Spark as part of our distribution, the most popular Hadoop distribution, for about 1.5 years now, since version 4.4. We're about to ship version 5.5 pretty soon. We launched Spark training quite a while ago. In fact, we just announced 4 new Spark training courses at Strata Hadoop World about a month ago. And have written, when I say we have written a book, I really mean 4 other people, our data scientists. Sean Owen is here, for example, on Spark. So we are very heavily invested in Spark and committed to its success in the big data market. Not only do we support it and work on it, but we have contributed, we think, quite a few important innovations in the last couple of years. Here are some of them. I'm not going to read all this, but as you heard yesterday from Barclays, from Intel, from others, Spark is a very important part of the big data ecosystem, but certainly not the only part. It has to integrate with the other open source frameworks that our customers rely on, and it has to integrate with the applications and tools that they use to do analytics and data processing. And that's a lot of the work that we've been doing to make Spark fit well into the enterprise environment, which is really our bread and butter. After 2 years, Cloudera has, we're approaching about 700 paid enterprise customers at this point. Over 200 of them are using Spark today, and the majority of those are using Spark in production. So we feel like we have as much experience as anybody seeing what Spark can do in the enterprise market and making sure that we're meeting the expectations of our customers, many of whom are very demanding, not only of Spark, but of Cloudera in general, insisting on enterprise quality, security, management, governance, all of the things that they expect from any data management system. So that's really what we've been working on. As we talk to all these customers and work with them and help them, we see emerging patterns of use. I think you've heard about a lot of them at this conference and past Spark summits. But these are some of the most popular use cases that we see. I don't think any of this will be a big surprise. Predictive analytics is obviously something that's very important. Stream processing. We have a lot of customers using Hadoop and Spark in general just for speeding up ETL of all sorts. So these are really some of the most popular use cases. And usually, Spark is co-installed with other frameworks in our system. So it's, in our case, very rarely used all by itself. It's used in conjunction with search. It's used in conjunction with interactive SQL through Impala, with HBase or with Hive. So again, the integration of Spark into our enterprise data hub architecture is critical because our customers are trying to solve very complex problems using Spark and all of the other data processing tools that we provide. But there's always things that they want that don't exist yet. So these are some of the things that they are really, I would say asking is a polite way of putting it, really demanding of us. So number one is security. And this doesn't apply just to Spark, but to our whole stack. These days, it's obvious security is probably the most important feature in any type of data system, especially when, as we're promoting the idea of putting all of your data into an enterprise data hub, into a Hadoop cluster, so that you can then preserve it both for history and for analytics and for real-time processing. It must be secure. So we're putting a huge effort into security. And performance. Spark, of course, is a very high-performance system. but our customers, as they scale it up, integrate Spark with all of the other frameworks, they really are demanding that it work just as well as the other systems that they might be augmenting or even replacing. And then lastly, this is a very complicated world. The world of Hadoop and Spark is extremely complicated for customers, and one of the big values of Cloudera and of all the companies in this market is that we try to make life simpler by providing management tools and governance tools, and that has to continue as you add Spark to the mix. So recently, about a month ago, at Strata Hadoop World in New York, we announced 2 new open source projects that are relevant along these lines. And I'll talk about them very briefly here. Record service is the first one I'll mention. This is a way to enforce access control policies in a consistent way across the stack. Today, in our solution, policies are really framework dependent. You might have to implement different policies for each framework. Data can be stored in HBase or HDFS, and you might have different policies for access for data in those frameworks. And then depending on how you're accessing the data, whether it's through Spark or Impala or Search, you might have to implement different policies there, and it's just very complex for our customers. So record service is a layer, if you think of it, between the data storage and the data access method, and the idea is to make the enforcement of access control consistent and easy to implement across the system, no matter where you're storing the data and no matter how you're accessing the data. So we're very excited about that, and we hope that that makes life easier for our customers and helps them to implement more secure systems. The second thing we announced last month was a new storage framework for the Hadoop ecosystem called Kudu. We found, and I think all of you who work with Hadoop probably know, the 2 methods that were available have been HDFS and HBase. HDFS was great for storing arbitrary data of essentially any type and for doing large-scale analytics on that data. And HBase was great for high-speed serving and updates, data that needs to be updated. Of course, you can't update the data in HDFS, so there was a lot of customers that we were working with that have the problem of trying to do analytics on fast-changing data, and it's very complicated to implement in the Hadoop ecosystem, as many of you probably know. So Kudu is intended to fill that analytic gap by providing a place to store data when you require fast analytics on fast-changing data. It's not a replacement for HDFS, and it's not a replacement for HBase. It really is something that would be implemented when you have a use case that has those requirements. There are still going to be plenty of use cases where HDFS is the best implementation to store data, and there are going to be others where HBase is really the best solution. But we think there's a very exciting gap in the middle there, and our customers, so far, the response to Kudu has been great. Both of these projects, Record Service and Kudu, entered beta a month ago, and if you would like to participate in the open source community for either of them, you should get in touch with the people involved. We are excited about both and inviting people to contribute very actively, so please get in touch with us. So in conclusion, I think the main thing that we want to communicate is that we do agree that Spark is probably the replacement for MapReduce. We have been committed to it for a couple of years. We have invested a tremendous amount in it. We have, I believe, 4 or 5 committers at Cloudera today and are looking for more if there's any that want to join. We think we're doing everything we can to promote Spark, to make it part of our customers' solutions. Our customers are demanding it. They're very excited about it. And we're excited that all of you are helping to contribute to it. The key thing that we're focused on as a company is providing value to our customers. One thing we've learned in the years we've been around is that technology for technology's sake is not that exciting. Our customers really want to understand how they can use this technology to get business value. It's a confusing space, and we do our best to try to explain it. But the more applications that you all can build that get value, deliver value for customers, the better. And together we can all help the enterprises who are adopting this at great speed get more value out of it. So with that, thank you very much. Come by our stand if you'd like to ask questions. We have a lot of people here, and I appreciate your time this morning. Thank you very much.
Thanks a lot. Thanks a lot, Alan. Great to hear about Cloudera's commitment to Spark and the long-standing commitment at that. Next up, we have a developer in the Spark project, and not just any developer, one of the lead developers, actually a lead architect in the Spark project. Reynold Shin is a co-founder at Databricks, and he has been with the Spark project for a very long time and has helped lead the design and implementation of some of the most important components. Before Spark SQL was called Spark SQL, there was a project that was called Shark, which introduced SQL into the Spark stack. And Reynold was a leader in that project and continues to be a leader on kind of all main core component, and many of the main core components of Spark. So it's a real privilege to hear Reynold during a keynote talk about a look ahead at the Spark development. And let's welcome Reynold to the stage.
All right, thanks for coming. So in the next 20 minutes or so, I'm going to share with you some of the major developments in Spark that happened in the past few months and also going forward. I figure we'll actually go nerdy a little bit, going back to our engineering roots, and talk about even some of the internals that might be quite different from the other keynotes we have here. For a lot of you have already seen this stack diagram of Spark. At the core of it, you have the Spark core engine that sort of exposes the RDD API. And on top of it, people over time, the community have built a variety of domain-specific libraries, including SQL, streaming, MLlib, and GraphX for graph processing. However, when I think about the development, I actually have a slightly different view of the stack diagram. I think this stack might be a better way to actually represent a lot of the development that's happening. And what do I mean by it? In this stack, we'll actually slice a line in the middle to cut Spark in half into the front end and the back end. So the front end consists of user-facing APIs that actually normal application programmers interact with daily. And the back end is what's responsible for the distributed execution of the Spark programs. So some of the concrete examples of the front end and the back ends are the RDD API, the data frame API, the machine learning pipelines, and the APIs in GraphX would go into the front end. And the back end includes a scheduler, which is responsible for how you dispatch different tasks in the distributed engine, the shuffle operation for data exchanges, and all the variety of physical operators in Spark SQL. All of those go into the back end. So the last 12 months actually witnessed some of the most active developments in Spark, the history of Spark since the project started. And there's a lot of major changes to both the front end and the back end. In particular, to the front end, there's data frames. There's the new data source API that actually makes Spark play nicely and integrate extremely well with a variety of different data sources in the existing ecosystem. And there's also the R new language front end. For the new data scientists already familiar with R, and machine learning pipelines. In the back end, we started the project Tungsten about 6 months ago, and there's also a lot of other changes that happened. So in the remainder of the talk, I'm going to zoom into two of the changes, data frames and Project Tungsten, and try to connect them, even though the two are similarly orthogonal concepts. So first, data frames. Spark data frames, as most of you probably already know if you're sitting in this conference, it's essentially a data frame abstraction, a scalable data frame abstraction for both single node and distributed setting. It exposes the API that's very similar to the data frame API in a variety of different programming languages and a single node. So for examples include the Python pandas and R dplyr. As a result, it's actually much easier for new data scientists and programmers to learn this new API. In the past, when we talk about the RDD API, you sort of have to understand what functional programming is before you can use Spark. But with this new data frame API, it becomes much easier to use and get started. However, data frames actually goes a lot deeper. The significance of data frames actually goes a lot deeper than just the front-end API exposed to the users. And in order to explain that, I have to first explain sort of how the RDD API is being executed. Programs returning the RDD API is being executed in Spark. In the RDD API, the API essentially expects user-defined functions, or sometimes you might call them lambda functions or closures in the respective programming languages. So for example, you have a Java API or Scala API would take in the closures. And then the closures are operating on sort of opaque Java objects that Spark doesn't really understand, as Matei hinted at in yesterday's keynote. So in order to actually execute these functions, and in order to actually pass objects to these functions, we have to run everything in the JVM, rely on exactly the same type of objects we have. Same thing goes for Python. If you write a PySpark program, what you will pass to Spark is the Lambda functions in Python, and those expects Python object as inputs and Python object as outputs to those functions. As a result, the only way we can execute them is to run them in the Python process. Now, let's go to the DataFrame API. The DataFrame API is actually fairly different. The way it works is when you're programming the DataFrame API, you are essentially specifying the way the logical semantics of your computation in a domain-specific language. So when you do 1 + 1, it's not really passing the JVM bytecode or a Lambda function to Spark. It's actually constructing an expression that indicates 1 + 1. And all this gets transformed into an intermediate layer called a logical plan. And then, if you've gone to Michael's talk yesterday about the Spark SQL, the logical plan goes through a relational optimizer called Catalyst to be optimized, and then a Catalyst generates actually the plan for the final execution. So this is actually the backend of the backend, which is the physical execution plan. So if you look into actually the DataFrame implementations for different variety of languages, they actually look fairly simple. And the reason is they're really just wrappers around the logical plan, this intermediate representation. As a result, one of the benefits of the DataFrame API to Spark, not necessarily to the end users, is it's actually much simpler to build new language frontends using the DataFrame API. For example, the Python DataFrame frontend was actually built over the course of a weekend by one of our engineers in about 2,000 lines of code. Of course, it's expanded over time, but that sort of explains how simple it is to build this whole new language API. And similarly, the R API took about only 1,000 lines of code. And as I know now, there's actually a lot of new language frontends that's being built by the community, including Haskell and Clojure and all of those. The second benefit, which some of you already seen in the slide, is performance. When you use the RDD API, when you use Python, because the Python RDD API has to be executed using a Python process across a cluster, Python natively runs slower than the Scala or Java. However, in the DataFrame API, because all the front ends are really just wrappers, converting them to the same logical plan, and then the same logical plan gets turned into a different physical plan for execution. So they really are all running the same code under the hood. As a result, you actually get the same performance for all the different languages we have in Spark: R, Python, Scala, Java, and even SQL. Now, next, Project Tungsten. In order to explain Project Tungsten, I have to sort of walk through history of the last 5 years a little bit. When Spark first started, it was, I think, in late 2009, early 2010. And we're going to take a look at the hardware resources that were available back in 2010 along 3 different dimensions: storage, network, and CPU. So in 2010, most of the world were running on spinning disks. And each of the spinning disks can probably pump out about 50 to 100 megabytes of throughput per second. And the predominantly data center networks are running at 1 gigabits. And CPU was around 3 gigahertz. Now, fast forward 5 years, 2015. What are you buying in your own data centers? Or what are you using in the cloud? In 2015, SSDs are becoming very common. As a matter of fact, in order to find a non-SSD instance on Amazon EC2, you actually have to look pretty hard to find one. Each of the SSD can pump out about 500 megabytes of throughput. And 10 gigabit networks are very common. And as a matter of fact, 40 gig networks are also becoming increasingly popular. CPUs, actually, on the other hand, hasn't really changed that much. The frequency of CPUs really hasn't changed, even though the density and the number of cores have increased a little bit. Now, when we first started Spark, because network and storage were the primary bottlenecks, we spent a tremendous amount of effort optimizing network and storage in the past 5 years. And as a result, when we actually profile most of the Spark applications, we realize they're all CPU bound. if you take a look at your hardware monitor, resource monitor, you realize you're not saturating usually your disk or SSD throughput, and you're not really saturating your network bandwidth, and your CPU is spinning at almost 100% full. Sometimes even things as simple as just reading data, scanning data to decompress your compressed data could saturate the CPU. So Project Tungsten is started about 6 months ago, aimed at substantially improving the CPU efficiency of Spark applications through 3 different methods. One is dynamic code generation, or we call it runtime code generation. This is our Spark to actually generate very efficient code, bytecode for execution, to eliminate all of the possible virtual function overheads and boxing of data structures in the JVM. And the second is to rewrite a lot of internal algorithms to employ variants of them that's much more cache efficient. And as a result, most of the time, Sparks are reading from the L2 and L3 cache of the CPUs rather than reading from memory. And last but not least is off-heat memory management. If you have profile Spark application before, often you realize a lot of performance actually goes out of the window because of the JVM garbage collection. By actually actively managing our memory ourselves in Spark, Spark actually knows more information about the application and can manage it better than JVM does. Now, the interesting thing about the Tungsten project is all the 3 actually requires knowing more about the semantics of the application, including sort of the layout and the structure of the objects you have in the program. That was actually pretty hard to do in the RDD API. Now, the interesting thing is, with the data frame API, Spark actually knows almost about everything that it needs to know in order to optimize this program further. And as a result, the Tungsten project is really only enabled by a lot of the work in the data frame API, including logical plan idea and the relational optimizer. Most of the Project Tungsten work, or most of the initial phase of Project Tungsten work, has been merged and is already available in Spark 1.5, which will release in September. There's actually going to be a lot more work coming in 2016. Now, let's look forward a little bit to 2016 and see what are some of the more exciting things that's coming. I picked 3 things that's actually really exciting about me personally. And you actually, as soon as I explain them, you realize they're actually a continuation of the 2 of the things I just pointed out, data frames and Tungsten. So the first is the dataset API that Matei kind of alluded to yesterday. When we first released data frames, a lot of people were really happy. A lot of new data scientists told us, oh, I don't have to spend hours learning about functional programming anymore. I can now just get started with Spark. However, we also started getting a lot of requests over time. And one of the most popular requests was, data frame is great, but I have my existing libraries that have specific objects or class types that I expect, and I want to use those libraries. How can I use them? And the number 2 request was, I want my type safety in Scala and Java. Data frame was great. You have the API that's already native in R and Python. There's not really types there. But when I'm writing a very large application across many different teams, I want stronger type safety. Give me that. And that's also actually Martin hinted at. So dataset API is actually a new experimental API we're introducing in Spark 1.6, which will be released in about a month. It essentially provides a typed interface over data frames, and as a result, also over Project Tungsten internals. What it does is it allows you to define essentially arbitrary Java objects or Scala objects as you want. In this case, have a Scala case class called person. And then you could read in a data frame, and then you can convert any data frame directly into this new abstraction called dataset that's typed just by calling .s and passing it the class type. And once you have a dataset API, you could actually apply a lot of the functions that's available on the RDD API directly to the dataset API. For example, filters, you could run reduce, you can run group bys. And also, you can easily convert it back into the data frame API just by running aggregations or using existing functions that's available in data frames. Now, some of you might start wondering, what really is this thing? I just spent a bunch of time explaining why it's hard to optimize arbitrary objects and arbitrary opaque JVM functions. So what's the benefit of this thing? And the reason is the magic really lies in this concept called encoder. In the dataset API, there's actually implicit encoder that you need to specify. And most of the time, if you're using Scala, it's infer automatically for you. And this encoder essentially tells Spark what this data type is and how we can map it into the tungsten types. So we can actually pack all these data types or the specific objects in memory in a very optimized way and leveraging the existing tungsten backend. I don't have time to go into a lot of details for this, but we actually grabbed a really exciting Jira number, Spark 9999. So if you search for Spark 9999, you can find a lot of details about this new dataset API and how the encoders work. And the first experimental version will be released in about a month. And this probably will become dataset plus data frames will become, I would say, the main abstraction going forward. The second thing I'm really excited about is streaming data frames. If you pay close enough attention, you realize Spark, we have the data frame support. Spark SQL already natively runs data frames. Machine learning pipeline is running on top of data frames. Spark streaming, however, really doesn't have a lot to do with data frames yet. And Spark streaming, or streaming data frames, just as the name indicates, is really to push the data frame concept also to Spark streaming. In order to provide a much easier to use API that combines, I think, batch streaming and interactive data analysis over streaming data. And one of the nice things about the data frame API is we have this unified data source API that we can actually read data in from a variety of different sources, even though they look, in terms of programming call, they look almost identical. This will also apply and carry over to the streaming data frames work. We have a unified data source and data syncs API for streaming data frames, and we also, because of the use of data frames, that Spark Streaming will be able to actually leverage a lot of the work that's going on with Project Tungsten. And last but not least, we have gotten a lot of requests about out-of-order data support. This is data that arrived much later than when they were generated. We will be adding native support to that for Spark Streaming data frames. And I want to end this talk with just the very last item. And before that, I have to sort of just show some hardware trends again. In the beginning of 2015, Microsoft announced having a VM support for up to 448 gigabytes of RAM on a single machine. And just a couple of weeks ago, Amazon Web Services announced support for a new VM type that will be available next year, up to 2 terabytes of RAM on the single node. So 2 terabytes of RAM in a single node. This effectively means a lot of the data for big data problems can actually fit onto a single machine. Another thing that's fairly interesting is in the middle of the summer, Intel and Micron announced this new technology called 3D XPoint. And 3D XPoint has 3 different kind of attributes. One is its latency is almost as slow as DRAM. And its capacity, or just the cost of it, is almost as cheap as solid-state drives. And last but not least, it's byte addressable, which means you could actually address any bytes in the 3D XPoint storage, making it much more similar to memory than solid-state storage. As a result, you could really view it as a new extension for memory. So now you have access to almost the size of SSDs, but in a memory fashion and latency. And all of this is really just showing you that hardwares are becoming more and more powerful, and a single node machine can become a lot more powerful. As also shown just in the Dell booth outside. Now, unfortunately, a lot of software needs to change in order to actually leverage some of these newer technologies and to leverage some of the power of the new single node systems. It doesn't actually just work by running Spark or running a Python program or running an R program on a larger machine. You realize at some point getting diminishing returns because the software can't really keep up with the hardware. That's one thing that's really exciting about the data framework and the Project Tungsten work, which is now, because we can capture the semantics of the computation in the different language front-end that all gets consolidated into this logical plan, we could actually generate using code generation in Project Tungsten, different backends for different runtimes. That's optimized for those runtime. So today, in 2015, Spark runs in the JVM and runs well, probably up to hundreds of gigabytes of RAM on each of the node. But tomorrow, it's very possible Spark can actually run a variety of different technology backends, including LLVM, leveraging the vectorized instructions in the modern CPUs, or leveraging the 3D crosspoints, just based on this concept of logical plan and code generation. So just to end my talk, there's only one takeaway if some of the stuff were too geeky for you. Just remember that data frames and its sibling datasets API will become sort of the new abstraction that permeates a lot of the stacks in Spark. And all the components up there, SQL, Python, R, streaming, graph, machine learning, will all be running on top of data frames and datasets. And they will all get executed in this new Tungsten backend that can selectively be optimized for a lot of different runtimes. Thanks. I think that's the end of my talk.
Thanks a lot, Reynold. I really like the new taxonomy, front end, back end. Hadn't seen it before. Makes it very easy to think about where development's going. And also the hardware trends at the end. I think the no keynote session is actually complete until you see some slides with hardware trends on it and how Spark will adapt. I'm excited about our next speaker. Patrick McFadden from DataStax is an evangelist for Apache Cassandra. Patrick is going to share with us an assertion, and I hope convince us, or I assume provide some backup for a relatively bold claim about the relationship between Spark and Cassandra. Not that they're just friends, the two projects, but that they are actually lovers, with the somewhat provocative title, Apache Cassandra and Spark, an amazing Apache love story. Patrick?
Oh, thanks. Now I got to prove that. I appreciate that. That was not the intent of this talk, to make this a provocative story, but OK. I'm going to try to figure out where I'm going to put that in. Well, good morning, everyone. My name is Patrick McFadden, and so I work for a company called DataStax. We're the company that just loves Apache Cassandra, but we also love Apache Spark, too, and I'm going to prove it to you, hopefully. I have to. So here's what we can just take as a base assumption. Cassandra, established, really good at storing a ton of data. I love this quote right here. I see this all the time because I'm in the Cassandra community, but you can assume people at scale are probably using Apache Cassandra because it was built to do that, and great. So, and this is kind of a funny segue. Hello, Reynold. Spark is really good at analyzing a ton of data, and that's a really interesting combination when you put them together like we see now. And that's what we've done at DataStax, is we build the Spark connector for Apache Cassandra. And that combination has been really powerful, and some of the neat things that are happening inside, not only in community, but in industry, because of this combination. So what has been the community response to this? This is about 1.5 years ago that we released this. It has been absolutely overwhelming. This is a picture from a talk that I did at Strata a few weeks ago. Do you notice that there's people standing? The talk was about doing time series analysis using Apache Spark and Cassandra, and standing room only. And this is what we see over and over and over. Whenever I start talking about analyzing data on Cassandra using Spark, this is the kind of response I get. And it's not just, wow, this seems like a really buzzy thing. No, they're really trying to solve some problems. So what problems do we have? What are we trying to solve with this combination? So this is a typical use case for Cassandra. And that's where I always like to start with these two things together. So let's say we have an IoT application, weather station collecting a lot of data, that sort of thing. You're dumping this high-velocity data into an Apache Cassandra cluster. Great. You're probably serving it up for a mobile application, for a web application. That is a very typical use case for Apache Cassandra. Now, what happens now whenever I need to analyze that data? Aha, that's when we bring in Spark. And enriching that data is what it's about for when we add Spark with Cassandra. Because a lot of times we're collecting data at such a high speed, it's difficult to do things like roll-ups and putting in the data that you can use on your mobile phone. Think about like a high and a low temperature for the day. Well, in addition to that, Spark jobs running overnight is going to do things really interesting for, say, in the batch. But even more important is that what's happening now. And that's where we bring in Spark Streaming. So this is a very typical use case where we see a lot. And this is, you can repeat this over and over, where we have Spark Streaming analyzing this data in the stream, dumping it into Cassandra at the speed that Cassandra can work at, and then you do the Spark jobs afterwards to roll it up and do that sort of thing. So you can look at most use cases, and they follow this pattern. Now, why is it that I have two different data centers here, one running Cassandra and one running Spark? And this is what we've done to make it work well, is Cassandra is built around, it was first thing it was built around, its first principle was replication. Replication is not something you mess around with Cassandra, because that's what it does really well. So when I have data pouring into that transactional work center or workload, and it's going into onto this side of my cluster, that's going to be high-speed data. It could be millions of writes per second. I'm serving up that data in milliseconds. That's a really transactional workload. But as that data is going into the transactional workload side of that data center, at logical data center, it's automatically getting replicated into the analytics cluster. So wait a minute, hold on. Automatically. This means now that the jobs of Spark jobs running on top of Cassandra can be manipulating data that's coming in real time without ETL. OK, let me repeat that, because I saw some disbelievers. No ETL. I don't know if you've ever done ETL in production. It sucks badly. It loses data. It's expensive. And it takes, I mean, sometimes when you lose that data, you don't know it. So doing ETL is really, for me, it's very 1999 when I did that. It takes me back to my Oracle days, which gives me PTSD. So no ETL now, as I enrich that data in the transactional side, or in the analytics side, as I'm manipulating the data and saving it back into Cassandra, that can get replicated back into my transactional side, and I can serve it up on my mobile phone, on my web app, what have you, without, again, the ETL process getting in the way. So this is an awesome combination, and this is how we deploy it with DataStax Enterprise. DataStax Enterprise has a suite of really cool things that are added to Apache Cassandra, but the analytics, our part of our analytics game is really about what we do with Apache Spark. So I've given you the use cases, and I've heard this because I travel around a lot. I do a lot of talks on this. I get this a lot. Oh, that's just a lot of talk, right? No one's doing this. There's some obvious jokes here, but no one's doing this in production. This is a big dream of a bunch of nerds that are doing things that no one put into production. You're maybe right. No, you're not. There's a little company in Washington. They were a startup a while back, and they're really doing well now. They're doing this in production today. That company is called Microsoft. This is a real use case. They also have a little product you may have heard of. It's called Microsoft Office. Yes, Microsoft Office uses Apache Cassandra and Apache Spark in production. And it's a very cool use case. Typical problem. They're doing event data, a lot of event data, 10 terabytes a day of event data. That's a terrifying problem. And to solve that problem, you have to have the right tool. And that it's always increasing. And that's even more terrifying if you're in a production trying to solve these problems in a big production environment, especially one that has a bottom line like Office. So this was the quote that I love. This is the one that makes you start searching for solutions that work. Whenever you have, oh, we're going to be doubling this every 8 months, I'm getting another job. And this is another issue that they're facing with. It's like, we are now in this global economy with data, and they have to think about where their data is. And Microsoft, being a global company and having users around the world, they need to make their data available to users wherever they are. And they have quite a bit. Microsoft has 19 data centers in Azure because they want to be closer to users. So here's the setup for this. This is the way that they do it. I'm taking this right out of their presentation, but I mean, if you look, this is kind of what I showed you before. Hey, here's a bunch of data coming in. It's going to Cassandra. We're using Spark to analyze it. The bottom cluster there, 200,000 events per second, and that number is going to get bigger. Oh, everybody's got their phone up now. That's a real material number. Now, that will probably grow to 500,000 and 1 million probably by next year. And they're ready to grow with that because they have 2 technologies that scale at that. Great. Microsoft also has a problem that, very timely, that I'm here in the EU because of this problem. This just happened. I don't know if you saw this. It used to be okay for US companies to bring data into the US from the EU under this safe harbor provision. Well, the Data Protection Commissioner said, nope, not allowed anymore. This is not a good deal for people that are working with data in an international sense. But Apache Cassandra has an option, or as a feature, can help you manage that. I'll give you a quick example. So if I set up a product catalog, which doesn't have any personal data, which isn't underneath those data protection laws, that's something I can replicate around the world. That's not a big deal. So I set up my replication factor in 3 different data centers. I have one in Germany, one in Ireland, and then one in Northern Virginia. And those are now replicating 3 times in each place. Awesome. That's not a problem. But what if I have personal data? I don't let it cross those borders. Well, you can set it up so easily with the replication so that replication is 0 in the US. So now that data is guaranteed not to cross the border. This is a configuration. This is auditable. You can show in an audit event that this is the setup for our cluster. So this does help quite a bit with data protection laws, and Microsoft would use it. There are others that are using it. It's pretty cool. So how about an example a little closer to home? I don't know if any of you from the UK, but you probably use this. British Gas. So they have this really cool little thing called Hive Active Heating. It's a mobile application. It's a thermostat in your house. And if you're familiar with Nest, that's a really cool little thing. 300,000 customers. This is a 200-year-old company that's modernizing quickly. They have to realize the 21st century is here. And so they're building this. So I love this statement here. It's very typical. It's the, wow, I have a lot of data coming. And it's typical in the case of these Internet of Things problems, which it sounds like a hypey term, Internet of Things. We're doing that. We're putting IP addresses on random things, like light bulbs. My light bulb has an IP address. I have to plug in my book. Welcome to the 21st century. This should look very familiar, but this is a copy and paste scenario. But in this case, it is for their Hive Active Heating. They have the thermostats reporting to a hub. They have the boilers reporting their information. This is in every home, and that data is going into the data center and being analyzed in real time. This use case right here, I could point this out to a lot of different production use cases, but this is very compelling. British Gas is very public about what they're doing here, and the things that you can get out of that data, the nuance, if you know that the gas is on, what can that tell you about someone's home? It's a little creepy sometimes, but I like it. You data scientists are probably getting really excited now, aren't you? You could figure out little things like, hey, you left your heater on when you walked out of your house because the mobile application that serves it knows where you are. That's kind of cool. You know, Google bought Nest for $3 billion. Why do you think they did that? You think they had a board meeting and they said, you know what? We need a thermostat. Let's pay $3 billion for a thermostat. No. I have a Nest in my house. Guess who knows when I'm there or not? Nest. It's pretty creepy, but Google loved it. They want the data, and that data is real time. And so this is what's the kind of use cases we're seeing, because analyzing that data, there's real value in that. So hopefully I showed you a couple really legitimate use cases, zero hype, real money, and this scenario is amazing, but it's not a handshake, right? It's not a handshake at all. This is a love story. So thank you very much.
Thanks a lot, Patrick. I'm convinced 10 terabytes a day, Cassandra and Spark at Microsoft on Office. That's all I need to hear. It's not just Spark and Cassandra. The whole theme of the morning, I'm really impressed so far, actually, about Spark and everything else. Not too surprised, I must say, but actually very impressed. Spark and Scala, Spark and Cassandra, Spark and the new technologies and hardware that are coming out, like 3D XPoint. It's very inspiring. And that's not all. We have our final keynote of the morning, which is yet again about Spark and something else. The perfect story, in fact, or maybe we could say that this is the perfect ending to a morning about the Spark Love Fest. And what better place to do it than in romantic Amsterdam? So the final love story, if I put it that way, is Spark and Hadoop. And there's no better person to tell it than Arun Murthy, who is a co-founder at Hortonworks. And I've known Arun for some time now. He was a mentor of mine when I interned at Yahoo. And at the time, he was very busy building the core of Hadoop. And since then, he's gone on to build many other core components inside the Hadoop ecosystem, including Yarn. He's here to tell us about how Hadoop and Spark are perfect together. Welcome with me, Arun.
Morning, everyone. I do talks all over, but honestly, back to Björsch, this is one of my absolute favorite venues. Especially the glass hall right next door. Really, really fun. All right, so you've heard a lot of love stories today. It's actually sort of good to take a step back and at this point maybe thank somebody who's very, very key for all of the entire Hadoop ecosystem, Spark, and so on, right? That's the ASF. The Apache Software Foundation is the home for all these projects, and I want to take a time out to thank the ASF, because without the ASF, none of us would be here doing all these cool things together. So at Hortonworks, we really think of this whole ecosystem, Hadoop, Spark, and so on, as the data operating system. Now, if you look back in the history of how computing's come along, it's now pretty clear that data is one of the most, if not the most tangible asset that you have, and you want to do everything to actually manage it, operate it, analyze it, right? And what we at Hortonworks every day get up and say is, the vision is that we want to be able to allow every single end user. You don't need these sort of guardians at the gate, right? You want every single user and application to be able to access all the data and share it with all the users and do all the analytics you want, right? And to do that, you need many, many things, right? You need to start with a storage platform. That's HDFS, which you can store all this data, structured, semi-structured, unstructured. Then you need resource management so that you can actually build different applications and more workloads, bring them all together in a common platform, right? It's not enough just to do these two things. You have to have sort of the key features like security and operations and governance and metadata management and so on. And last not least, you absolutely need a great API for developers, because let's face it, developers, you guys in the room are the sort of the lifeblood of the system, and making sure that you guys have the access to the best and the most intuitive tools for developing is really, really key, right? So that's why we come to Spark. And why we love Spark at Hortonworks is that it really presents a really, really simplified user interface for end users, whether it's streaming, whether it's analytics, whether it's ETL. And really, for me, the key about Spark, which I get excited about, is the fact that it's really, really made for data science. If you look at how people are looking at data today, we've gone from looking at transactions, what did the customer do on my site, what did he do with my product, to now trying to predict what he's going to do. And that's the real value of data science, right? We've talked about predictive analytics for a long time. It's sort of a buzzword. But I think the really key aspect that people don't realize, and that's the exciting part about Hadoop and Spark, is that you can now do predictive analytics at scale at a very, very fine granularity. You can do it for every single person in this room, every single person in this world, because that's the way you make every single customer feel special, right? In the past, you had to you've had to sort of take shortcuts. You have to do sampling, you have to do clustering, and so on. But really, the value with data science and Hadoop and Spark right now is that you can do all of these at a very, very fine granularity, right? So with that, what Spark has done is sort of democratize machine learning. In the past, you had to buy some commercial products and so on. But really now with open source and sort of democratized machine learning, you really, really have a wide open field. Last not least, community is really, really key, right? You guys would not be here but for the great community that's engendered around Spark. Particularly, again, want to thank the ASF for it. And overall, it's really helping to realize the value of the data operating system. So Spark is becoming one of the absolute key tools in the box here. So it's fun to talk about the technology aspect, but really, I think it'll be interesting to see what people are actually doing today with Spark, right? This is a small sample of what our customers at Hortonworks are doing with Spark. Now, WebTrends is somebody who's probably very familiar with. They've been a very, very early Spark adopter. In fact, they've adopted Spark for such a long time, and they've contributed that folks like Sean, who's at WebTrends, is one of the contributors at Spark. So what were they doing before, right? In the past, they were just doing batch analytics to do WebTrends analytics. They provide a service, WebTrends, so that you can go in and put some cookies and so on, and they'll give you analytics on top of what people are doing on your site, right? So in the past, they were just doing batch analytics. They migrated over to Spark a little bit early, and they had a separate Hadoop cluster and a Spark cluster. It was really hard for them to manage their infrastructure, right? So today, you fast forward, what they do now is they have a single shared cluster. They have Yarn to manage their other workloads like Hive and so on, and they have Spark streaming to actually ingest all these events. They're talking about billions of events. 10 billion events a day at 20 millisecond latency. So all these events are clicks and ad impressions and so on. And then they use Spark ML for predictive analytics. What they're trying to do is actually they're trying to classify users and say, is this user going to abandon, in this session, is he going to abandon this product or is he going to buy that product? Now, if you feel like he's going to abandon that product, maybe you want to give him a coupon or a discount or whatever it is, right? And they do this now in real time while the sessions are active. So as you can imagine, this is really, really valuable from a revenue perspective for both WebTrends and their customers. Let's talk about something even more mainstream. Let's talk about insurance. So as you guys know, claims reimbursement is a really, really big deal, right? So when a claim comes in, you got to figure out if it's fraudulent, if it's under-provisioned or over, and so on. And in the past, a customer of ours, in the Midwest of the US, they would actually use R, right? So they'd use R on a single machine, so they'd sample the data set down, and they'd use something like a random forest implementation to do analytics on a really, really small scale, anything that can fit in one box, right? Now, the other problem they had is they really couldn't do things like text analytics. To give an example, if somebody had written, I am now making a fraudulent claim, in the claim itself, they would ignore it because they didn't have the means to process it, right? Funny. Now, what they do today is they've actually migrated from R to run all of this on Spark, right? So now they can use both text analytics and other analytics capabilities in the same platform. And more importantly, they can do it at scale, right? And you're talking about literally tens of millions of dollars that they're saving today because of the fact that they can do it at scale with all of the sort of more modern analytics functions they're using today, right? So really, really key use cases that we're seeing in the platform today. Now, let's talk some more. Now, these are a couple of use cases I talked about, what we've done in the past, what is happening right now. So entity resolution is a big deal. So you go to healthcare, we work with a number of hospitals, a number of big insurance firms and so on, the healthcare providers. They get a lot of feeds. They get a feed from a healthcare provider, they get a feed from a doctor, and you have to figure out if it's the same user. It might be John Smith and Jay Smith. You got to figure out it's the same user. This, it sounds easy, but it's a really, really tough problem, right? Now, there are absolutely no standard packages available to get this done, and you also need to be able to take off additional features to be able to disambiguate. So, for example, if Jay Smith and John Smith have the same address, you now have a better, you now are more sure that it's the same person, right? So again, this is something that we at Hortonworks want to contribute back to Spark as a more general purpose solution rather than you guys having to put together all these algorithms on your own, right? And we want it to be sort of an extensible framework so you can do both supervised and unsupervised learning. Similarly, in finance, we have a customer, one of the really big financial firms. They use HBase today as sort of their store of records. So as you have all these stock quotes come in, they store that in HBase. You have company events like key events like earnings, stock splits, and so on and so on. They store all that in HBase, right? Now they wanted to open this up so that their customers can actually do end-user analytics based on a Spark-based platform. And to do that, we've been working with them so that we can actually give them a really, really fast path to get Spark to deal with HBase. So with HBase, you can do things like predicate pushdown inside as a co-processor. If you guys are familiar with how Apache Phoenix works, that's what it does. You actually write some code which actually runs in the region server. And we want to be able to expose that through to Spark in a first-class manner, right? So it's a sampling of different use cases. So let's talk a little bit about what we want to do given this scenario of what our customers are doing, right? I always find it useful to actually build software in the context of what people are actually doing. So with that background, some of the work we're doing is obviously innovating at the core, right? All the way from we now have an HDFS in-memory tier, so you can now use Spark RDDs and data frames and so on, and can be cached in the in-memory tier. We want to do better resource management with Yarn. For example, one of my colleagues helped to put in dynamic executors with data locality for Spark when Spark comes in with Yarn, right? Security is a big deal. Governance is an even bigger deal. As Hadoop becomes sort of the storage platform of record, you want things like metadata to be automatically captured as your Spark applications run. And that's what you do with Apache Atlas, which is, again, a governance and a management framework for data, right? Last but not least, operations and deployments is huge. So we've been doing a lot of work with Cloudbreak. Maybe many of you are familiar with Cloudbreak. We actually acquired a company based in Budapest, Hungary. And what Cloudbreak does is it makes it really easy to deploy Hadoop clusters. So a lot of our customers are now using Cloudbreak with Ambari to deploy a data science cluster. So a data science cluster on Google or a data science cluster on Microsoft, along with things like Apache Zeppelin, right? Now, as you innovate at the core, clearly, like I said, data is one of the key assets. We want to make it easy to access all sorts of data in the Hadoop ecosystem through Spark. So we've done a lot of work in the past. With Spark 1.5, we have Hive ORC, which is sort of the standard storage format for Hive. That can easily be accessed through Spark now. Similarly, HBase, we talked about the work we've been doing for the financial guys. And last but not least, we at Hortonworks acquired a company called Onyara, which does Apache NiFi. You may have heard of it. And NiFi is great for the IoT sort of use cases, right? Where you can actually collect data from the edge, from your devices like mobiles and cars and so on, right? So we want to be able to hook up Spark so that the NiFi streams can easily be accessed and processed in real time. Last but not least, one of the areas we really care about, and we spend a lot of time at Hortonworks, is on data science acceleration. And data science acceleration, for me, has many, many aspects. One is, we want people to be able to get data and sort of visualize it very, very fast, right? Most data scientists will tell you 80% of their time is spent cleaning up data, finding the right data, and so on, which is where Zeppelin comes in. Zeppelin is a sort of a notebook, web-based notebook. I'll talk a little bit more. Similarly, we want to be able to provide great data science libraries, not just individual algorithms like LDA and so on, but sort of full packages so that users like yourself can actually spend as little time as possible getting your entire workflow worked up through Spark, right? Similarly, we've been investing a lot in the core machine learning capabilities, sort of one versus rest, serializing machine learning pipelines and data loaders for public sets. The last one is really important. There's a lot of data, there's a lot of public data sets, and it takes a lot of time to load it. So we want to be able to make it really, really easy for you to access all these data sets. For example, in Europe, you can find lots of public data sets about geospatial data, right? So if you're not familiar with Zeppelin, this is what it looks like. It's sort of an open notebook. There was, again, sort of, this came from a small company in Korea, NF Labs. They might be around here. So again, a shout out for them. It just, again, shows the value of the community. So every day we see new innovations come from all over the world. It's really exciting to see. So what is Zeppelin? So Zeppelin is just a web-based notebook for analytics. and you can do things like data visualization, experimentation. It's completely Spark-based, right? Last but not least, like if we talked about the core contributions we're making, one of the things we're really excited about is Magellan. Now, you might have gone to the talk yesterday from Ram Sriharsha, my colleague at Hortonworks. He's the guy who's been behind the project. Now, what Magellan is it brings really, really simple and easy geospatial analytics to Spark, right? Now, why is this important? As you can see, geospatial data is really, really, really useful in a lot of contexts, right? So if you want to serve an ad, you want to know where this person is. Is he in front of Macy's? Is he in front of Tesco, right? That's one. You want to do things like traffic analytics. You want to do crime analytics. All of this is really, really enhanced by having geospatial data. Now, what Magellan does is it makes it easy for you to take all these different kinds of geospatial data, parse it out, and bring it in a standard format like polygons and so on, right? It gives you a simple and intuitive syntax, so you can actually now do simple geospatial analytics without having to worry a lot. And remember, there's a lot of issues with geospatial data, right? Because every different country looks at geospatial data in different formats. What you find in the US is different from what you'll find in Europe. And Magellan attempts to sort of harmonize all of this, so that as a data scientist, you don't have to spend too much time, munging data around, right? And there's a bunch of blogs and so on that you guys are welcome. Ram and I are going to be in the booth over, so if you guys have questions, feel free to come by. So let's actually put all of these things together. Right? We talked about the work we're doing in data science. We talked about Zeppelin. Let's see how easy it is to put together, right? So let's talk about the use case. The use case is something you may be pretty familiar with it, which is I'm an Uber driver, right? Where should I hang out to get the most revenue, right? Because you're all over the city. Where should I hang out to actually make most revenue, right? Now, here's what you could do with something like Zeppelin, right? First, you load this data up, right? As you can see, Magellan and Zeppelin make it really easy to load it and sort of visualize it. And you sort of join it with take your Uber data. Uber actually, it's really great. They actually publish an anonymized data set. So you can take that anonymized data set, join with the geospatial data, and you can start to look and say, at what timestamp, what trip started at what neighborhood, right? So next, what you can do is you can say, which Uber trips are passing through which neighborhood, right? So you can now join all this data, join your trip data with your neighborhood, and sort of group by and say, who is going where, right? Similarly, you can say, all right, now that I know where the trips are passing through, let me look and see which neighborhood has the most Uber trips which are starting, right? So it shows that in south of Market, which is Soma, you actually get a lot of trips starting, right? Similarly, you want to now check how many trips start in Soma but also end in Soma. So you can now go back and say, OK, I've got a bunch of trips starting in Soma, a bunch of trips ending in Soma, so maybe I need to hang out at Soma, right, which is south of Market. With that, hopefully you get a sense of all the work that's happening in the Hadoop ecosystem with Spark. And again, I want to take this opportunity to thank Databricks for having us over, and also all you guys for taking time to come talk to us. With that, thanks.
Thanks very much, Arun. Before we break for our morning mid-session, just want to make 2 announcements. First, you'll be returning to 3 different sessions for the rest of the day. The developer track is in this room, data science next door, and there's a research track between now and lunch, which will be upstairs. If you go out and to the right, you'll be able to get directions from the helpful folks pointing the way. And second, check for various vendor office hours. I know that a lot of the Spark committers are hosting office hours this afternoon, so if you have Spark questions and want to sit with a committer, please go ahead and do that. And finally, to wrap up the keynote sessions for the second day, this is the last time we'll be all together in one room. I just wanted to thank everybody here. We've done Spark Summits in a number of cities now, and the community here is top-notch. It's very impressive to see the kind of spirit and the excitement and everything that you've brought, that we bring to the table here in Amsterdam. So really, I think we deserve to give ourselves a round of applause in conclusion. And have a great rest of the day and summit. Thanks a lot.